So yes, I'm Greg Sullivan from Dover Microsystems. I'm going to give you a very, very brief high-level overview of how we're implementing fine-grained information flow-oriented confidentiality and integrity on a Rocket-based RISC-V SoC. So pretty much every security product or technology bows to confidentiality and integrity in some way. Probably everyone's aware of the long-standing definition of information security in terms of the CIA triad. Today, we're not going to be talking much about availability. But for instance, any sort of compartmentalization, what we call compartmentalization technologies such as the T approaches or physical memory protection or virtual memory for that matter, divides the world up into these different sized compartments, and one compartment can't read another compartment's data, so that's confidentiality, and one compartment can't write another compartment's data, so that's integrity. But we take a much more fine-grained approach, applying confidentiality and integrity-based metadata to each word in the system, and then flowing that metadata along with the values as they flow, potentially through many different compartments. So our approach is to first define the terms confidentiality and integrity as policies, which are a set of rules. And I've greatly simplified what I present here versus the details of the system that we're implementing, just to make it digestible in a short amount of time. All of these policies, confidentiality and integrity, and other policies that we can implement with our system sort of have these 3 or 4 basic components. The first is, how does data get to be tagged, for instance, confidential in the first place? And for confidentiality, we might, for instance, say that a trusted decryption function, anything coming out of that should be considered confidential. Or maybe we have a trusted key generation hardware or software block, and we say that the key data itself should be considered confidential. Then these policies talk about flow. The overall arching approach that we're taking is called information flow control. And the flow says, as values combine with other values, go to memory, back to registers, back to memory, et cetera, processed by the ALU, how does the metadata flow with these values and change over time? And for confidentiality, you want to say, for instance, that if confidential data is combined with other data, confidential or not, the result should be considered confidential. Then it's information flow control. What's the control? Control is enforcing certain constraints with respect to the data and the metadata. And in this case, we'll say the most basic confidentiality is we identify, again, using metadata, which areas of memory should be considered publicly visible. So publicly visible output, for instance. And the core central rule to confidentiality is that confidential data cannot be written directly to publicly visible memory ranges. And finally, any interesting security policy will have some notion of privilege. And in the case of confidentiality, you want to indicate that possibly if confidential data is successfully processed by a trusted encryption engine of some sort, that can strip the confidential classification and make the data accessible and therefore able to flow out of the system. For integrity, the rules are similar. If you're familiar, this is not a surprise, but the flow rule is sort of the dual of confidentiality, whereas confidentiality is sort of profligate. Integrity is fragile. So if you are tracking where data came from and whether it's been modified, and you call that a high integrity value, if the data is modified during processing, it's no longer considered high integrity. And with respect to control, for integrity, you want to identify the consumers of information, consumers of data, whose integrity you care about. And at that point of consumption, such as, for instance, if you have an encryption function, you want to designate that the key parameter was emitted from a trusted key generator and hasn't been modified since. So those are the control points. And I forgot to mention where initialization happens. Suppose you might, again, the key generator produces keys, and you might want to not only consider them confidential data, but you also want to track their integrity through processing. Also, a very common use of integrity is insisting that data has been processed. So untrusted data comes into the system and must have passed through a trusted sanitization or validation function, for instance, before it is allowed to go into a database system, for instance. So that's where the data, the provenance or whatever is initialized. So again, all of our policies and confidentiality and integrity in particular have these different parts. There's flow, it's information flow control, and we say it's fine-grained because it's every word in memory, and it has metadata attributes associated with it. And these metadata attributes are defined, as I'll describe shortly, with these software-defined policies. So obviously, this is just a really quick overview of what we do, and I do refer you to the literature on information flow control for confidentiality and integrity is vast. There's very formal treatments of it. There's static and dynamic approaches to information flow control. And there's also some mostly academic hardware implementations that you come under the heading of DIFT, dynamic information flow tracking, where they typically add a couple of bits to the hardware and track them through track these taint bits, as they're called, through computation. The issues with the current academic implementations tend to be, first of all, that there's just a few bits, and also that adding these bits to the microarchitecture in the pipeline is disruptive, and so it's hard to use a commercial, highly optimized CPU implementation, for instance, and just add on those bits. And what our approach overcomes both of those issues. So again, an extremely high-level, quick overview of the technology that we use to implement this fine-grained information flow control. It's called CoreGuard from Dover Microsystems. And looking at the bottom of the screen here, you'll see we start with a RISC-V host processor. In this particular project, it's a Rocket-based RISC-V host processor. We grab instruction trace with data addresses as well into hardware IP that sits on the chip next to the processor, grabbing the instruction trace at runtime. And for every instruction, we do several things. We, first of all, map the RISC-V instruction itself to a generic, smaller set of abstract instructions that we call shapes. And we also look up the metadata for all of the data referenced by that instruction. So the instruction itself might have metadata, any registers, and any referenced memory. And then we look up in a rule cache whether that particular combination of metadata with this particular sort of instruction is allowed, and if it updates the metadata anyway, that's how we do flow. And if it's disallowed, then we send an interrupt back to the host processor. In general, what we ship is these three, what we call base policies: fine-grained memory safety, and stack. So memory safety stops buffer overflows and overreads, which is a fine-grained memory system notion of confidentiality and integrity. And then there's a stack protection policy that prevents return-oriented programming attacks, which were mentioned by a previous talk. Fine-grained RWX, where we can give each word, even in a binary, different read, write, or execute permissions. But the reason these are the base set of policies is because for a given runtime, like FreeRTOS or Zephyr, the programmer doesn't have to say anything. They just use CoreGuard and everything happens automatically. And from the user's perspective, the software developer's perspective, in the upper left hand, we show that we basically add one more step to the basic build process. So we take the ELF binary A.out here, produced by whatever tool chain you're using, run it through what we call a policy linker, and the output of that is a map from physical memory addresses to initial metadata, so that when the application is loaded, we know how the world of metadata starts. In this upper right hand, we note that for memory safety, for instance, the relevant metadata, of course, is what regions of memory a given pointer is allowed to reference. In this particular project that I'm describing, that we're implementing these new policies, confidentiality and integrity, it's, as I've mentioned before, Rocket RISC-V based 64 RV64GC. I should note that CoreGuard also is, we have implemented on 32-bit RISC-V platforms. So, it's actually runnable on small systems. Anyway, the interesting things about this SoC are it has an embedded FPGA block and one or more AES blocks in hardware. And we use these confidentiality and integrity policies, among other things, to track the integrity and confidentiality of the components of the bitstream as it comes into the system, is possibly inflated and manipulated before it makes its way to the eFPGA fabric. And also any of the data coming out of the AES blocks, whether it's key material or encrypted or decrypted data, is also tracked using these policies. I'm going to give you just a quick sort of lower level view of how to view this approach of fine-grained information flow control. Every instruction, so we have here on the lower right a load word RISC-V instruction. As I mentioned, each instruction is mapped to what we call a shape. It's sort of an abstract instruction, and there's many fewer of those even than there are in the RISC-V reduced instruction set. And furthermore, every word in memory, in our case on a 64-bit RISC-V system, it's every 64-bit native word in memory, has a corresponding set of metadata values, which we represent really as a pointer to those values. So in this simplified example, there's IO memory might have public IO as its metadata, and the current register. And then when there's a load, the current value of the output register is metadata value is referenced. Possibly any metadata on the instruction itself is all sent to a rule. At least semantically, there's rule matching going on. Of course, this is all optimized in terms to a rule cache. There's no actual sequential processing going on, and the rule says is this particular combination of shape and metadata allowed? If so, is there an update to the metadata in the output fields, or is it a violation, in which case an interrupt is sent to the hosted CPU. This is a sort of a overly detailed slide, but the idea is to see that while in the below the dotted dashed line, there's a pipeline of RISC-V instructions, loading from memory, processing with ALU and more memory traffic, and then more processing going back out to sort of memory mapped IO. There's sort of a parallel pipeline in the CoreGuard world, where instead of host native application values being processed, there's metadata values being processed and updated, where the RISC-V instructions are given semantics via the standard RISC-V definition. The semantics of these shapes, these abstract instructions, is given by the set of policies that are currently installed on the machine. So for instance, we'll just look at one, the last store word, and in the encrypt function, for instance, the instruction itself might have a tag which gives it declassification authority. And there's a rule that says if I have a store instruction that has a declassification authority, then the output is tagged as public, regardless of whether it was public on the input. I'm going to give you a quick view into these. What does it mean to write these policies? We have a domain-specific language called, creatively enough, the Dover policy language. And all the policies have these sections that I basically outlined earlier. There's at the bottom here, there's for confidentiality, there's how does the data get initialized. At the beginning here, we actually define the language of tags, metadata values that we're going to manipulate, so we can distinguish between private and public memory mapped IO. Private values, or for lack of a metadata tag, would be a non-private value, and privileges assigned to trusted instructions. There's always an assertion. There's usually some legality, explicit failure rules, as we call them, which in this case says if it's a a store to publicly visible memory and it's a private value, then it's a violation. And then there's the flow rules. I'll point out one that's a little subtle here. So as I mentioned before, we tag at a 64-bit native word granularity. So what happens if this load sub pub.io, this is, I know, impossible to read in real time, but the slides will be available afterwards. So what happens if I'm loading from a public area of memory, but the register that's going to receive the value is currently contains private value, and I'm loading a subword that is not the entire 64 bits. Maybe I'm loading a byte or loading a half word. This rule says, well, the bits that are in the recipient, the destination register, should remain tagged as private because there's still some remaining private bits, so to speak. For integrity, very similar. I'm running low on time, so I'm going to skip details, but I'm certainly happy to answer questions later. Roughly speaking, for integrity, if anything modifies a word or even part of a word that is tainted as trusted in this simplified version of the policy, then it's no longer considered trusted. So in this slide, I go through some code that exercises these policies, and again, it's a little much to digest in real time, but basically if it's a green box, it says there's no errors flagged. But if I'm trying to print private data to public output, it's an error. This last red box is pointing out that if I overwrite a public 64-bit value with just a little bit of private data, then then the whole thing's considered private and is an error. Similarly, for integrity, we have a function called run command, which insists on trusted data. And the sanitize command function is privileged such that it can take untrusted data and sanitize it and taint it as trusted. I'm wrapping up now. I wanted to give a quick overview of how this sort of fine-grained information flow control approach to providing confidentiality and integrity compares to the most common approaches. Certainly today, we've heard a lot about what we call in general compartmentalization approaches, that is the T approach or WorldGuard or physical memory protection or virtual memory for that matter. And there's nothing wrong. I don't want to say that there's anything wrong with those approaches. They're perfectly valid and can be done with low overhead, although there's typically context switching overhead for those approaches that there's not with CoreGuard. But of course, these compartmentalization type approaches act sort of as gates. Is this data allowed to go from this compartment to that compartment or not, and so forth. But when the data goes through the gate, is allowed through the gate, there's no further tracking of where did that data come from, where is it allowed to go, those being the two critical notions of integrity and confidentiality, respectively. And furthermore, these approaches tend to be coarse-grained. That is, a compartment, whether it's a process or a trusted operating system, as we just heard about, still contains millions, possibly tens of millions of instructions and lots of data that it has access to. And why would you think that large chunk of software is not vulnerable to software exploitation? And there's no good reason. In fact, probably is. And so if the attackers can disrupt, can destroy the confidentiality and integrity of the data within every compartment in your system, why do you think you've got system-wide confidentiality and integrity? And in fact, you probably don't. Which, again, not to say that it's a bad idea. It's perfectly good to be able to say, this code should never access data over here. If you know that's true, you should be able to write it. On the other hand, sometimes you want to be much more fine-grained. I wanted to point out that memory safety, which the Cherry project, for instance, does very, very well. We're not hearing about it today. Also, CoreGuard has a memory safety, is in many respects a close proxy to application level confidentiality and integrity, right? But it's not the same thing. So you can have a confidentiality violation at the memory safety level that would be a false positive because it didn't actually violate application level notion of confidentiality. and ditto for integrity. However, the advantage of memory safety is that it can be automated. So our motto here at the bottom of the screen is, if you should always use what you should be able to specify whatever confidentiality and integrity requirements are relevant for your system at whatever granularity you know and care about. So if you only care that no data in this so-called trusted zone can be, the no data in the so-called untrusted zone should be ever writable or readable from this code in this trusted zone, or vice versa, fine, if that's all you care about. But if you really care about where data came from or tracking where specific chunks of data are allowed to go, then you want to have this option for fine-grained information flow control. So that's kind of our motto. And I want to make sure that people know, even though the world has done compartmentalization-based virtual memory and so forth forever, you can do much better than that. That's really the message from this talk. Furthermore, as opposed to other different DIFT type approaches, we don't have any additions to the instruction set ourselves in CoreGuard. And you can have, as opposed to this very simplified example that I walked through today, you can have an unlimited number of confidentiality and integrity labels. Much more interesting, a lattice of confidentiality and integrity is usually what's referred to for multi-level security and so forth. Anyway, that's it. Sorry for such a hurried talk, but I tried to cover a lot.
Thank you, Greg. We have quite a few questions in the Q&A if you want to take a look at them.
I certainly will.
Do you see them? Can you see them there?
I'm just closing out everything here. Where did it go?
Yeah, down at the bottom in your Zoom.
Yeah, no. I had it in a separate window that then got covered up. Is there metadata for each 64-bit word, or do you do ranges? Or do you do? We do all of that. So yes, it's a very good, what we try to do, especially for smaller systems, is we try to reduce the overhead that we're going to impose in terms of memory. And yes, typically, for instance, for IO ranges, we'll have ranges that all have a homogeneous metadata tag. So where the policy is clear that data, for instance, is fixed according to where the data resides in memory, sort of it's associated with location versus the value, then we can cut corner, we can reduce space usage by not worrying about those being updated. We have something called a tag map table that maps any size range down to individual 64-bit words to metadata. So we do compress, we have a highly compressed representation. The naive implementation would essentially double your memory at a minimum. And we have we require more like 25% of memory for metadata maintenance on the side. If performance or space overhead, so I just mentioned the space overhead. Metadata, we say roughly 25% of whatever the application data memory range will be needs to be reserved for maintaining metadata. Performance-wise, certainly for the base policies, there's essentially zero overhead because all the rules are compressed and fit into this rule cache. And if you get a hit in a rule cache, then the CoreGuard system keeps up with the host RISC-V system. And so there's essentially zero overhead in that case. And the system itself is quite configurable. You define what the size of your rule cache is and so forth, and even the tag granularity. But our default configuration, we have a RISC-V reference platform that we distribute. There's no overhead for the base policies, plus the integrity and confidentiality policies that I mentioned today. But you can always add more policies, and eventually you would potentially miss in the cache, and then there's more optimizations beyond that I can't get into. Was there other?
Looks like the others were maybe for our last speaker. So anyway.
Okay. Well, I'll just do one more. There was one about how does it compare to Cherry. Cherry is a capability-based, which again, like information flow, has a very long history, and as security people, we should all be aware of that. Cherry is very, very good at memory safety. Arguably, they're farther along than we are, but they don't do information flow. So we take an information flow approach. That's kind of the central part of our approach, and we can apply that to memory safety, stack safety, and obviously fine-grained information flow, confidentiality, and integrity. That's sort of its sweet spot. Cherry has these capabilities represented as so-called fat pointers, where every pointer in the system has in that pointer, the so-called fat pointer, also a representation of where in memory it can access with what rights. And so it's extremely good at memory safety, but not so good at information flow stuff. So it's an extremely good product and project, and I can only the best things to say about it, but it's different in that respect.
Okay. Perfect. Thank you so much, Greg. Appreciate it.
Thank you.